So a very good afternoon again. So this will be the third lecture, and the first two slides are same only, just to give you a feeling that this is the serial number third going on chemical measure trace and ultra trace analysis. So in this, we have already seen terminologies and vocabulary, sample storage, preparation, separation, chromatographic. Today, we will be looking into the principle and applications of spectroscopy in chemical measure trace and ultra trace analysis. So the content of this lecture is the principle and application of UV visible spectroscopy, principle and application of atomic absorption spectrometry, then atomic emission with flame, plasma, and electrical discharge sources we'll just see, and then mass spectrometry. So what is spectroscopy? Spectroscopy is a branch of science that studies the interaction between electromagnetic radiation and matter. Now, spectrometry and spectrometric methods. So this is spectroscopy is the interaction between EMR and matter. And what is spectrometry? It is the measurement of the intensity of radiation with a photoelectric transducer or other type of electronic devices. So whenever we are doing some spectroscopy, to get the concentration, we must do a spectrometry also. So the major class of spectrochemical techniques are absorption, where you can have atomic as well as molecular absorption. Then emission, so atomic emission we will be looking into. Then luminescence, that is fluorescence, phosphorescence, and chemiluminescence. Scattering, Raman scattering, turbidimetry, and nephelometry. So these are the various spectrophotometric techniques. Now, you all must be knowing the electromagnetic radiation. So it is from gamma rays to radio waves. So now in this total electromagnetic radiation, with each range, various types of spectroscopy are possible. As we have seen, spectroscopy is nothing but interaction of EMR with matter. So like gamma rays, if it interacts, then nuclear phenomenon will happen. X-ray, then core level electrons will get excited. UV visible, then it is valence electrons. Infrared, vibrations happens. Microwave is rotation and electron spin resonance. And again, radio waves, NMR and all spectroscopy are there, which deals with nuclear spin. So in this lecture, we'll be focusing into the ultraviolet and visible radiation. So which ranges from around 190 to 700 and small of near IR, so around 900. So from 190 to 900 nanometer we'll be focusing into. So, and one thing I want to just tell you here, that even mass spectrometry does not involve any electromagnetic radiation. Still, it is known as spectrometry. And it is because maybe its analytical process and data output closely parallel to traditional spectroscopic methods, and therefore measurement in mass in analytical chemistry is also referred to as mass spectroscopy or mass spectrometry. So now, throughout the spectroscopic techniques, what is the signal? It is the photon. Photon as a signal source. So a spectroscopic measurement is possible only if the photon's interaction with sample lead to a change in one or more of the properties of electromagnetic radiation, such as its energy may change, intensity may change, frequency may change, and so on. So in absorption spectroscopy, a photon is absorbed by an atom or molecule which undergoes a transition from lower energy state to higher energy state, and thereby it absorbs the incident radiation. Now, the type of transition depends on photon's energy. For example, absorbing a photon of visible light promotes one of the atoms or molecules' valence electron to a high energy level. And therefore, there will be decrease in intensity, which can be correlated with its concentration. So just for a pictorial representation, this is the ground state, and here some energy is falling on this. So this electron will absorb that energy and go to the excited state. Here also, and now that excited state electron, it is not stable for a long time there. So it will again come back to ground state, releasing the same amount of energy, whatever E has absorbed. So this is the emitted energy. So this is the simplified energy diagram that shows the absorption and emission of a photon by an atom or a molecule. When a photon of energy strikes the atom or molecule, absorption may occur if the difference in energy between the ground state and the excited state is equal to the photon's energy. Otherwise, absorption will not occur. So that is where resonance absorption it is known as. So an atom or molecule in an excited state may emit a photon and return to the ground state again. So this photon energy is equal to the difference in energy between the two states. So this is what is absorption and this is what is emission. Now let us see bit deep into UV visible spectroscopy. You all must have operated this instrument while doing your BSc or MSc, during MSc also. So this is where the absorption of light in the UV visible part of the spectrum, that is around 210 to 900 nanometer, that is near IR range, is measured by a small and tabletop instrument which is known as the molecular spectroscopy or UV visible spectrophotometry. The transitions that results due to the absorption of electromagnetic radiation in this UV visible region of spectrum are transitions between electronic energy levels. So generally during these processes, the most probable transition is from the highest occupied molecular orbital, that is HOMO, to the lowest unoccupied molecular orbital, that is the LUMO. You must remembering the concept of HOMO and LUMO, I suppose. Then now you can see this is the two energy states for a molecule state. This is the ground state and this is the excited state. Now you can see when some air radiation falls on the molecule, then it will absorb and go to a, and these are the vibrational states. These are the vibrational states shown here. So it goes to a higher vibrational state of the excited electronic state, and then it may come back by radiating or may come back by non-radiative transition, and which will increase the heat of the solution. Now you can see that the incident photon of UV and visible light have enough energy to cause transition between the different electronic energy levels. And for molecules, vibrational and rotational energy levels are superimposed on electronic energy levels. And because of many transitions with different energies can occur, the bands are broadened. So the broadening is even greater in solutions owing to the solvent-solute interaction. What does this mean? Whenever you are looking into a molecule, you can see if it is an electronic transition and it is getting transition is from ground state to excited state, then it should be not like a spectra, it should be a straight line, because from two states, it is happening in two states. However, instead of that, normally for UV visible spectra, we got a broad shape like this. This is because now this transition is not necessarily it will be from one electronic state to another electronic state. There is vibrational states. Here you can, the blue color are rotational energy levels, green color are vibrational energy levels. So they also are present in between. So there can be transition from any of this level. And therefore you normally for a molecular spectroscopy, you got a broad spectra. So which is pictorially represented here. Now, two important parameters or factors of terminology used in UV visual spectroscopy is that transmittance and absorbance. So when light passes through a sample, the amount of light absorbed is the difference between the incident radiation I0 and the transmittance radiation IT. So the amount of light absorbed is expressed in terms of absorbance. Normally you must be well acquainted with the term absorbance in case of a UV visible spectrophotometer or atomic exhaustion spectrometer. So what is absorbance? It is log I0 by IT. And what is I0? I0 is the incident radiation and IT is the transmitted radiation. So when it is transmitted through the medium with analyte atoms, it gets attenuated because the atom absorbs the incident light. So if you plot like absorbance versus concentration, then it will give a straight line, and therefore this relation is normally used in analytical purposes, whereas transmittance versus concentration, it is an exponential decay, and therefore because of exponential curve, it is normally not used in quantitative analysis because error will be more. So this is the absorbance. Mathematically, it is represented as log I0 by IT, or which is minus log T, and percentage transmittance. Always the incident radiation is taken as 100%. So we calculate the transmittance in terms of percentage. So that is IT by I0 into 100. Normally, this type of absorption spectrometry obeys Beers-Lambert's law. What is that? It is nothing but absorbance equal to epsilon CL, where epsilon is the molar extinction coefficient. You all must be knowing it is a constant for absorbing species and defines the absorption of the species at a particular wavelength. And when the concentration is moles per liter, and the path length, this L is the path length, which is in centimeter. So it is determined by the number and type of chromophores present in the molecule of the absorbing species. So this epsilon is constant for a particular system, but for different system it will be different. So now C is the concentration, L is the length of the light path through the sample. In case of this UV visible spectrophotometer, you must remember that there is a cuvette in which you are taking your sample. So that cuvette is normally the normal available cuvette are 1 centimeter. So that is the 1 centimeter is its path length. So absorbance is an additive property if more than one species are present in the solution or in your sample. So all the absorbance of the mixture will be summation of all the species present in the solution. So sometimes there is the deviation from Beer-Lambert. So you all must have observed if you are taking the concentration, whenever you are plotting a calibration curve, which is nothing but absorbance versus concentration. So when you go on increasing the concentration, there is a linear relationship, as you have seen here. There is a linear relationship between absorbance and concentration. However, whenever you are increasing the concentration, it does not happen that it goes on increasing linearly forever. So there is a deviation. Sometimes it is a negative deviation, sometimes it is a positive deviation. So where does that deviation occurs? So deviation from linearity are divided into three categories, namely fundamental, chemical, and instrumental. So just a slide of each of these points I want to give you it here. So the fundamental limitation is that the law is valid only for low concentration of analyte. You must remember the assumption or postulates of Beer-Lambert's law. At higher concentration, the individual particles of the analyte no longer are independent of each other. Analyte's absorptivity depends on the solution's refractive index also, and our solution's refractive index varies with the analyte concentration, resulting in deviation. For sufficiently low concentration of analyte, the refractive index is constant and Beer's law plots is linear. So this is the fundamental limitation. Now, what is the chemical limitation? Chemical limitation may occur if the analyte is involved in an equilibrium reaction. Say there is a chromophore HA. There is a species HA which is in equilibrium with its A minus in your aqueous solution. Now, both HA and A minus absorbs at the selected wavelength. Then the Beer's law is this one. So this is not a straight line equation, as you must be knowing. A straight line equation is nothing but y equal to mx plus c. But now mx plus c should be a constant. But now this is not a constant. The another term is not a constant. There is a variable epsilon. There is a variable concentration. So depending on equilibrium, it will be different. So it is not a straight line equation. So it tends to deviate. Now instrumental limitation, what is that? The law assumes that radiation reaching the sample is of a single wavelength. That is, it is a monochromatic source of radiation, because you must be remembering the definition of Beer-Lambert's law that when a monochromatic radiation passes through the sample. So it is not actually clearly monochromatic, because whatever best monochromator you use, it can select a few wavelengths, not a single wavelength will be selected. So even the best wavelength selector passes radiation with a small but finite effective bandwidth. Now, polychromatic radiation always gives a negative deviation, but the effect is smaller if the value of epsilon is constant over the wavelength range passed by the wavelength selector. Because for all these wavelengths, now the species, whatever is present in your solution, has a different epsilon value towards all the wavelengths. So there is a deviation. Now, stray radiation also is the second contribution to instrumental deviation. How? Because when there is a stray radiation is there, you know that absorbance is nothing but log I0 by IT. Now you imagine there is a stray radiation. Then it will be I0 plus stray radiation by IT plus stray radiation. But when the absorbance is very high, means when your concentration is very high, so the transmittance is low. That means IT is low. That case, the stray radiation plays an important role because stray radiation is fixed throughout the measurement. So when it is low concentration and IT is very high, then stray radiation does not make any effect. But when IT is low, so there is an effect or there is an effect of stray radiation, and therefore your absorbance deviates from linearity. Now let us see in a molecule when it is subjected to UV visible radiation, you get a absorbance peak. So or some absorption spectra. So where that is because there are transitions between pi, sigma, and n. So this is a typical transition giving for the formaldehyde molecule. So you can see there can be transition from your n to pi star or pi to pi star, or from sigma to pi star, and all this type of there can be there. So like I have divided it into three categories. For organic, what can be the most probable transitions for metal ligand complex, and for inorganic molecules. So for organic molecules, it will be sigma, sigma star, and sigma star, and then it will go to deep UV. And for double bonds or unsaturated system, because double bonds means pi electrons are there, so there it will be pi pi star, or if it is a non-bonding electrons are present, say oxygen or something is there, then it is a n pi star transition. Even metal ligand complex, in case of metal ligand complex, charge transfer transitions are there, because of which the complex looks colored. And inorganic molecule, you may be knowing that it is a DD transition is responsible for its color or UV visible spectra. So now this is a typical setup of UV visible spectra. So schematic diagram of a scanning double beam spectrophotometer. So a chopper directs the source radiation using a transparent window to pass radiation to the sample and a mirror to reflect radiation to the blank. So at the same time, the radiation will be passing to the sample and to the blank. So since it is double beam, so the blank contribution will be neglected during the same measurement, during the single measurement. And when there is no sample, it can be set up to 100% transmittance, and so on. So the photographic insert shows here you can see that this is the one module which is actually used for temperature control unit. If you want to do your sample in various temperature, then also modules are available like this. You can attach it with your instrument and you can do a temperature study of your system. Now let us look into the atomic spectroscopy. This is what is the molecular spectroscopy. So now let us go bit more detail to atomic spectroscopy, because molecular spectroscopy are very general and you already have learned it in your BSc and that level. So now we'll be looking into the atomic spectroscopy. So atomic spectroscopy is based on the interaction between electromagnetic radiation and atoms. Now in case of normal spectrophotometry, those are molecules. Now these are atoms. So when atoms are exposed to a source of energy such as heat or light, then what happens? Their electron can absorb energy and transition to higher energy level occurs. So upon returning to their original state, again the electron releases energy in the form of electromagnetic radiation. So now this emitted or absorbed radiation is a characteristic of a specific element. See this, whether an atom is absorbing or emitting, whatever wavelength is used, that wavelength is very specific for elements. It will be different for different elements because all the elements have different discrete energy levels, and therefore it is a signature of that element and therefore it can be used to quantify that element. So this is the basic principle of atomic spectroscopy. So according to quantum theory, atoms or molecules or ions have only a limited number of discrete energy levels. For absorption of radiation to occur, the energy of the incident photon must exactly match the energy difference between the ground state and one of the excited state of the absorbing species. Now these energy differences are unique for each species, and so a study of the frequencies of the absorbed radiation provides a mean of characterizing the constituent sample. Let us look into the case of a sodium. You have seen that there are sodium vapors like long back. Normally in the street light, sodium vapors are there. Sodium vapor lamps are there, which looks yellow. So in case of sodium vapor, you all know sodium has 11 electrons. So that is the electron configuration is 1s2, 2s2, 2p6 and 3s1. So now this 3s1 is its valence electron. So then when you are subjecting the sodium vapor or sodium atoms to a UV visible radiation, then what will happen? The 3s1 will absorb energy and it will go to the it will jump to the higher energy levels, higher electronic levels. So now you can see there is no vibrational or rotational levels associated with atom. Since this is an atom, it is a single entity, so there is only electronic level, no vibrational or rotational level. Now all the, as I have seen now, 3s to 4s is not possible because there is selection rule, delta L equal to plus minus 1. So therefore it is 3s to 4p or 3s to 3p, 3p to 4d or 3p to 3d. So those, all these transitions have different wavelengths. Just marked it, all these transition has different wavelength. And this 3s to 3p, which is the most probable transition for sodium atom. This we normally, while doing, we monitor this wavelength. This is the maximum probable line. So as I have told you, there is no rotational or vibrational level in case of atomic spectra. So you can see, you can have a look to this. These are very sharp spectra when we consider atoms. Sharp bandwidth will be of the order of 0.001 nanometer. Whereas in case of molecular spectra, since we have already seen there the electronic levels are associated with rotational as well as vibrational levels. So these spectra are quite broad because this is not only for electronic to electronic level, but electronic to many vibrational level or rotational level. So it is a broad spectra. Now, what are the different terminologies? Again, terminologies in case of atomic absorption spectrophotometry is the similar to same as the normal spectrophotometry, that is transmittance and absorbance. And again, some I0 fall on a medium where atoms are there, and then your IT will be there. And again, then absorbance versus concentration is a straight line. So we focus on this rather than focusing on transmittance versus concentration, which is a exponential curve. Now, what is the normal block diagram of a atomic absorption spectrometer source? That is, there will be a source because it is a atomic absorption. Whenever there is a term absorption spectrometry, means you require a source from which I0 intensity will be coming, which the atom or the absorbing species is going to absorb. So there will be a source, then an atom cell. Now here it is not sample cell, simple sample cell as in your case of molecular spectroscopy, where you are taking your sample in a cuvette, and in the cuvette your sample is present in molecular form. But here it is atom cell. Because it is atomic absorption, you need to produce atoms of your sample, which will be analyzed here. So now then monochromator to select the particular wavelength, then detector. And now sample introduction system. Since it is an atomic absorption, you need a specialized sample introduction system to produce their atoms out of the your sample. Say for example, you are detecting iron. In case of normal molecular spectroscopy, iron will be detected as either iron phenanthroline complex or iron thiocyanate complex. So the complex itself is a colorful complex, which absorbance will be there at some wavelength, and you will identify it. But in case of same atomic absorption, if you are going to determine iron, then it will be as iron atom rather than any complex. So you have to understand that concept. So now what can be the source in case of a atomic absorption spectrometer? As you may be knowing that in case of molecular spectroscopy, normally deuterium lamp for UV range and tungsten lamp is used for visible range. So in a UV visible spectrophotometer, now it will be deuterium as well as tungsten lamp will be there, and when your wavelength will be passing from 300 to above, so it will change to tungsten lamp. So that throughout the wavelength you can have a continuous spectra. But is that your source B can be used in case of atomic absorption spectrometer where the absorbing lines are very fine? Let us see it. So you can have a look. So this is the your output of the source. Say this is the output of your source which is coming after passing through the monochromator, and this is your absorbing line of your species. So in case of atomic absorption species, it is the absorbance when it is a broad spectra. If the source it will be a broad one, then absorbance will be very less. So we need normally a line source for atomic absorption, or line source is better than rather than a broad source. So let us for some mathematical calculation we will do, which will clear our concept that in case of atomic absorption, you will require a line source rather than a continuum source. So say you can take a case where the source line width is greater than absorption line width. So now you can, this is the source output. Just for easy calculation, I have done it in a square output manner. So you can have a look. This is the source output and this is your absorption profile. Say now the absorption profile, say you are looking into sodium atom. Now sodium atoms are there which have a very fine absorption line, and say the concentration is such that it can absorb 50% of the source output. So now source line width will be 0.1 nanometer, say. Absorption line width is lower than that, that is 0.01 nanometer. So now what will be the output is 10 units. Absorption is 0.5 unit. So detected light means whatever light reaching to the detector is 9.5 unit. So now if you calculate the absorbance by putting the formula log I0 by IT, so then now you see that this is the I0 and this is the IT. So it is 0.022 only. So you see then when your source output is broader, 0.1 nanometer is broader, then your absorption line width, it is 0.01 nanometer, 10 times broader it is, then your absorption output is only 0.022. Rather than in a case when the source line is equal to absorption line width. So in case of source line width is 0.01 nanometer and absorption line width also 0.01 nanometer. Then when it is 100% source output is 1 unit and sample absorption 0.5 unit. So the IT is 0.5 unit. So in this case, you can see the absorbance is 0.301. So for the same concentration, same 50% absorption only, you can see same 50% absorption. But when the source line width is more, then the absorbance you get is very less. But when source output is similar to the absorption profile, then your absorbance is quite high. So now let us take a third case where the absorption profile is lower than the source line width is lower than the absorption line width. So here in this case, the output of source is 0.5 unit, sample absorption is 0.25 unit. Now detected light will be source output, whatever the 100% minus 0.25 is 0.25 unit. So again absorbance if you calculate, then it is 0.301. You can see when the source line width is less than absorption line width or source line width is equal to absorption line width, absorbance is same, 0.301. Therefore, however, when the source output is broader, it is 0.022. So what do we understand from this? Is that for maximum sensitivity, the spectral line width of the source should be less than or equal to the absorption line width. So this is very, very important. So therefore, of different type of source is required in case of atomic absorption, which is known as the hollow cathode lamp. But recently, you can use a high intensity continuum lamp, but with a high resolution monochromator which can separate a very fine line from the source. So what is a hollow cathode lamp now? So the hollow cathode lamp is nothing, is built like this, where this is the cathode and this is the anode. Now cathode is made up of the material which is your analyte. So for example, you want to measure iron, then the cathode will be made up of iron. Now what happens here? When an electrical, now this you can see the sputtering, excitation and emission. What is this? This is the expanded picture of this cathode material. Now you can just have a look. when an electrical potential is applied between the anode and the cathode, some of the filler gas atoms are ionized. So inside this is made up of either quartz or glass, depending on your element to be analyzed. Now inside that, your inert gas, either helium or argon or neon, sometime also are they are present there, but at a lower pressure, 1 to 2 millimeter of mercury. Whereas the what is your atmospheric pressure is 760 millimeter of mercury. So at a lower pressure, they will be filled there. So now the positively charged filler gas ions accelerate through the electric field to collide with the negatively charged cathode and dislodge individual metal ions in a process called sputtering. So the filler gas will strike the cathode and then M0 will be there. So now the M0 will strike the, so the sputtered metal ions are then excited through a kinetic energy transfer by impact of the filler gas ions, and these excited atoms comes back to the ground state by emission of characteristic wavelength. So now when these excited atoms comes to ground state, they will emit their characteristic radiation. So if you are going to measure iron, so you will take a hollow cathode lamp of iron, so that in your atom cell, your iron will be like, by some means you will generate iron atoms from your sample, and now your source is of iron. So definitely its emission line will exactly match the absorption line of your analyte. So this is known as actually lock and key effect in case of a atomic absorption spectrophotometer, that is lock and key effect. So whatever is the emission line of your source is exactly equal to the absorption line of your analyte. Now, what is a continuum source? How can you use a continuum source? In case of continuum source with high resolution monochromator, you can use a xenon short arc lamp, which power is 300 watt. Lamp current 15 ampere, operating voltage 20 volt. Internal pressure, now it is 16 bar. Normally, your atmospheric pressure is how much bar? So it is in high pressure. Internal pressure when it is hot is 50 bar. So now its living time is like how much time it can work is 3000, more than 3000 hour. So the manufacturer is, it is a patented product and it is manufactured by some company GLE in Berlin. So it is a continuum source covering from 185 to 900 nanometer. It is used normally with a high resolution monochromator so that it can separate a 0.001 nanometer line out of this, so that atomic absorption can happen. And now its resolution is the high resolution monochromator has a resolution in picometer range. Okay. So now where the name like hollow cathode lamp, because the shape of the cathode is hollow, it is called as a hollow cathode lamp. Now the way it is hollow, because it needs to collimate. You can see now your atom cell will be here, as you have seen in this case of your atom cell, where atoms are there. Now source is here, hollow cathode lamp will be there, so that light has to cross just like this. So it should be collimated, rather than if it is a dispersed light, then not much light will be falling on the atom cell, and therefore you have to need a collimated beam, and which is done by the shape of the cathode. Now that, as I have told you, in case of atomic absorption spectrometer, one fundamental thing you need to do is you have to generate the atoms. Normally, when you are dealing with a sample which is in solution form, your analyte will not be in atom form. Say sodium chloride, if you are dissolving in it water, what will happen? Sodium plus solvated and Cl minus solvated. So they are in plus or minus form. So they are not as atom form, but we require atom to happen the atomic absorption. So depending on the formation of atoms, the atomic absorption can be divided into 4 types: flame atomic absorption, graphite furnace atomic absorption, hydrogenation atomic absorption, and then cold vapor atomic absorption spectrometer. So now let us see one by one each one. So now flame atomic absorption, here this is the hollow cathode lamp, and this is the flame sample. Now this is the monochromator. Now this is a detector. So in FAS, either you will use a AR acetylene or a nitrous oxide acetylene flame, because to produce a flame, you require oxidant and a fuel. So in case of AR acetylene, which is the oxidant, AR is the oxidant carrying the oxygen, and which is the fuel is the acetylene. So now this burner, nitrous oxide and acetylene. So here the oxidant is nitrous oxide. So acetylene, these two types of flame are used in case of your atomic absorption spectrometer. In air acetylene, the temperature is around 2500 degrees centigrade approximately, and it is very suitable for alkali metals, calcium, zinc, all the transition metals and all. Whereas the nitrous oxide acetylene flame is bit higher temperature at 3000 degrees centigrade. And so this can be used to do the refractory elements which are very much towards forming oxides. When they are heated, so they have a tendency to form oxides. So they require high temperature to break into atoms. So boron, aluminum, barium, strontium, etc. can be done by nitrous oxide acetylene flame. So now whether the burner head, what type of burner can be used in the case of your atomic absorption? Say normally you have seen a Bunsen burner in your lab when you are using a heating thing. So you have seen a Bunsen burner. How it looked like? It looked like this. So there is this is your flame. But whether this type of flame is they are sufficient for your atomic absorption to happen? No, normally in atomic absorption spectrometry, it is a slot type of burner. So there is a slot either 10 centimeter long or 100 centimeter long or 50 centimeter long. Slot type burner is there. So the burner head, two types of burner head depending on your flame. One is, as you have seen, one is air acetylene flame and the other one is a nitrous oxide acetylene flame. So now, depending on the flame which you are using, either you need to use your 100 centimeter burner head or 50 centimeter burner head. So burner head is decided based on two factors: instrument signal and safe operation of flame. Now, when like path length, now path length say it is just now in case of Bunsen burner, you see the path length is very less. So as you know, absorbance equal to epsilon CL. So if you increase the L, that means your absorbance will increase. That means you can go to lower and lower level of analyte. But whether this length can be increased indefinitely, like if you do it 1 meter of length, so it is not possible. So there is a limitation to that, how much you can increase the slot length. So finally, the slot length has been increased, and it is found that 100 centimeter for air acetylene and 50 centimeter for nitrous oxide acetylene flame can be done. So as I have told you that to increase the sensitivity, the slot length cannot be increased indefinitely. The main requirement for safe operation of flame is that the linear gas flow rate must be greater than 3 times the burning velocity. So above condition ensures that the flame cannot travel backward. So if the flame is traveling backward to your cylinder, then some explosion may have occur. So therefore, you cannot just increase the slot length. Burning velocity of a flame is the velocity at which the flame can travel. So burning velocity of nitrous oxide acetylene flame is greater than that of air acetylene. And therefore, the linear flow rate equal to volume, as you must be knowing, linear flow rate equal to volume flow rate by area of burner. Now, volume flow rate same for each gas, because you are maintaining the volume flow rate by using a regulator. So you can regulate that. So acetylene has around 12 liter per minute, and nitrous oxide air has around 24 liter per minute is the gas flow. So burning velocity of N2O C2H2 flame is greater than air acetylene flame. So therefore, to increase the flow rate, linear flow rate, the slot has to be decreased. So N2O C2H2 burner slot length is smaller, 50 centimeter than air acetylene flame length. So flame height is normally in the range of 5 to 10 centimeter. So now the case is that you have 100 millimeter burner head and 50 millimeter burner head. So now whenever you are using a air acetylene flame, you can use either of these two burner head. But when you are using a nitrous oxide acetylene flame, you can use only 50 millimeter burner head. The 100 millimeter, if you are putting, then it will not work. There is a safety lock and the instrument will not work. So this is the flame temperature. Now, how atom are forming in the flame. So let us look into the case how, for a particular solution when you are passing to your flame, what are the various process going on there and how the atom are forming. So when your sample is there in a volumetric flask, you have your sample. Now your sample is being passed to the flame through nebulization. What do you know nebulization means? Your sample will be mixed with your fuel and oxidant, and then it will micro droplets will be formed there, and then it will go to the flame. So there it is in the aerosol form, it will be going there. So what will happen in the flame? Because of the temperature, now it will be dissolution will be there. So your, say it is sodium chloride, then NaCl solid will form, then it will melt. So NaCl liquid, it will vaporize, NaCl gas, then it will atomize like Na and Cl. It is not Na plus and Cl minus as it was present in your solution, but now it will be Na and Cl. So now again temperature is there, so they will excited, or your by absorbing the light from the source, they will get excited to its higher energy level, and then your atomic absorption will happen. Sometimes it may ionize also depending on its ionization potential. If it is less, then it may ionize also. So now let us see what are the various interferences possible in case of your atomic absorption spectrometry. So very few interferences are there, mainly divided into two types, spectral and non-spectral. Any matrix component giving a signal at an allied signal is known as spectral interference. Very few, as AS use specific source for specific analyte. As I have told you, for iron, if you are doing, then you are going to use a iron holocathode lamp, and therefore the spectral interference is very low. Still, in few cases are known where you can face spectral interference. For example, say antimony you are doing. So now antimony has a wavelength of absorption is 217.6 nanometer, whereas lead is 217 nanometer. So if in your sample you are doing antimony and lead is present, so it may interfere because both are very close wavelengths. So these interference can be corrected by either background correction methods or by taking an alternate line, such as an alternate line for antimony is 231.1 nanometer, whereas lead it is 283 nanometer. So there are multiple lines, multiple absorption line available. You may take one depending on your free of interference. Now non-spectral interference, what is that? Any parameter which affects the formation of atoms comes under this category. So there are three major types of non-spectral interference: matrix interference, chemical interference, and ionization interference. Now let us just see what are these. What is a matrix interference? This is caused because of difference in sample and standard nature, like viscosity, acidity. So if there is a difference in viscosity, then while nebulization, your standard may have a different rate of nebulization, whereas your sample may have some different rate of nebulization. So now, as you know, this type of instruments are comparative instruments. Means you are taking standard first, then you are drawing a calibration curve, and then your unknown sample is compared to the calibration curve, and you are finding out the concentration. But when there is a difference in viscosity between sample and standard, and nebulization rates are different, so your standard may not correlate with your sample. So to minimize this matrix mesh, standards can be used. Now chemical interference, what is that? If the sample contains a component which forms a thermally stable compound with the analyte that is not completely decomposed by the energy available in the flame, or chemical interference will occur. For example, the presence of phosphate in calcium determination. You know, calcium phosphate is a very strong complex. It will not break at the temperature of your air-restrained flame. So therefore, as phosphate concentration increases, the absorption due to calcium atoms normally decreases. So there can be three ways to minimize such interference. If you have a prior idea that your sample contains phosphate in which you are doing calcium, so you can follow either of these three. So this is one typical example. There can be many such chemical interferences. So the thing is that you have to have a clear idea regarding your sample, your analyte, what are the metrics and all the things to take a wise decision while doing the analysis. So for this case, in case of calcium and phosphate, you can use a releasing agent like lanthanum or strontium. You add excess of either lanthanum or strontium to the solution. So what will happen there? Your calcium is in ppm range. It is in complex form with phosphate. Now when you are adding lanthanum or strontium, now the phosphate will complex with this because they are in a higher quantity. And so this equilibrium will revert back towards the atom form of calcium. So your calcium will be released for analysis, and therefore it is known as a releasing agent. Now, use of a protecting agent. If you are adding a chelating agent like EDTA, so EDTA has much more affinity towards calcium than phosphate, whereas at the same time EDTA is an organic complexing agent which has very low stability, like at higher temperature around 600 to 700 degree, it will decompose, so leaving the calcium free. So if you are adding EDTA to your sample, then what will happen? Now first, it will complex the calcium in preference with phosphate, and therefore your calcium will be at that temperature of your flame, it can form atoms because EDTA can decompose. Now, yeah, or else you can use a high temperature flame like nitrous oxide acetylene flame can be used for calcium determination. Now, ionization interference. This is often encountered in a hotter flame for more easily ionized elements like alkali metals, alkaline earth metals. You know that ionization potential is very less. So with that temperature of 2500 degree, they can very well get ionized. And once they are ionized, means their valence electron is getting lost. So like sodium, I show you in the previous slide, the sodium 3s to 3p is the most probable transition. But if sodium is getting ionized, then 3s electron is getting lost. So now there is no electron is there in 3s to give that transition of 589 nanometer, which is the most probable absorption line of sodium. Therefore, we have to suppress the ionization. That how it is to be done? It is done by adding, like if you are analyzing sodium, then add either potassium, rubidium, or cesium at a very high quantity, so that whatever energy from the flame, they will be diverted to ionize these salts rather than sodium, which is in ppm concentration, and therefore the equilibrium will shift toward the left side, giving you sodium atom. Now let us see what are the various advantages of flame AS and disadvantages of flame AS. So it is a robust technique, fast analysis time, very few spectral interferences, easy to calibrate, easy to operate, and above all, it is low cost. Even capital as well as running, both are low cost. However, it has poor detection limits for refractories, lanthanides, and actinides. As just I have mentioned, they tend to form oxides in flame, and therefore they have very poor detection limit. Use of flammable glasses, some accident may happen if you are not very careful. Then sequential in nature means one by one element, because for a particular analyte you have a dedicated holocathode lamp. So it is a sequential in nature, one by one analyte you have to do. So that is a very much disadvantage in nowadays where it is fast moving. Everything is fast moving, so sequential is very much not required. Now wastage of sample, because in this case you are using a nebulizer which from the aerosol which are supplied to the flame for producing the atoms in a very efficient manner. But in this process, now your 90% sample go to waste. Only 10% are going to get atomized. So wastage of sample is very high. Now prone to chemical interferences as the temperature is very low. So they are prone to chemical interferences. Just now we have seen few examples. So the next variation of atomic absorption spectrometer is the graphite furnace AS. By far the most advanced and widely used high sensitive sampling technique for atomic absorption is the graphite furnace. This has the detection limit in the range of microgram per liter, that is ppb, whereas in case of flame AS it is ppm. Now here it is ppb, means 1000 times less amount you can detect in your sample, and even sub microgram per liter level you can analyze in case of graphite furnace. So what is that? Rather than in case of a flame, there are graphite tubes, very around 2.5 centimeter length and 0.5 centimeter internal diameter graphite tubes are there. And this is the block diagram of graphite furnace atomic absorption. Now it is the holocathode lamp. This is the graphite tube, and this is injection port. This small hole is the injection port where only few maculator of sample has to be put. Then monochromator, detector, and signal processor. The components of this technique are the same as that of flame atomic absorption technique. Only difference is the sample cell or atomizer. In this case, the flame is replaced by a small cylindrical graphite tube of about 25 millimeter and long and 5 millimeter of internal diameter. So you can see some expanded picture of this graphite tube. Cross-sectional picture is given here, where this is the cross-sectional picture of your graphite tube. Here your sample is here you are going to deposit your sample. And how much amount of sample is required here? Unlike in flame AS, where minimum 5 ml of sample is required for one element, here you need only 10 to 100 microliter of sample solution. Few microgram of, if it is solid sampling, then you can even take solid sample here. So there are small boards to take microgram quantity of samples. Just have a look to this. So there it can be there. So few microgram of solid samples can be taken and quantitatively placed inside the tube. Normally through a sample injection hole located at the center of the tube well. The tube is heated through a programmed temperature sequence until finally the analyte present in the sample is dissolved into or dissociate into atoms and atomic absorption occurs. So this is the liquid sample, this is the solid sampling accessory for graphite furnace AS. Now, if we compare flame AS to graphite furnace, then here flame AS is the residence time is 1 millisecond, which is a continuously flowing system. Your sample is by nebulization, your sample is reaching to the flame, and with the flame they are getting washed away. So only if you calculate the residence time, then the residence time of the atoms in the light path of hollow cathode lamp is only 1 millisecond. Whereas in case of GFAS, it is 1 second, because it is a small confined tube and your sample you are putting inside discrete quantity of sample. It is not a continuous flow. Discrete quantity of sample you are putting, so and then you are heating it. So residence time is 1 second. Now sampling efficiency, as because of the use of nebulizer in case of flame AS, only 10% sampling efficiency is there. 90% samples are going to the drainage or waste away. Now, in case of, however, in case of GFAS, only a small droplet is putting inside the GFAS tube. So it is 100% sampling efficiency. So the total increase in sensitivity, here it is 1000 times, then here it is 10 times, should be 10,000 times. Factor of 1000 for residence time and factor of 10 for sampling efficiency. However, practically, if we see, then we found that it get enhancement is of 1000 times only. So this is because the background which increases along with signal. So now it is as your signal is getting increased, and therefore you can go to lower level to see in case of GFAS. So when signal is getting increased, the background also is getting increased. So because of the background, now the increase in efficiency is not 10,000 but 1,000. So background correction methods are must for GFAS technique. So now what are the various advantages of GFAS? It is better detection limit than FAS, minimal sample consumption, solids can be analyzed directly. Now disadvantages are high background, memory effect, poor precision than FAS, sequential, low sample throughput because of furnace programming. One analysis takes approximately 2 minutes, almost 10 times longer than FAS. Now loss of analyte during ashing, temperature gradient will be there. So these are the various disadvantages of GFAS. Now, because of the high background, as I have told you, we can use background correction methods. So there are various types of background correction methods that I'm not going to discuss in details. If you require, then I can send you the PDFs for that. So you can mail me if you want it. Then this is the continuum source background correction, G-band background correction, and Smith-Hipper correction. So for all this, I can send you the PDF files or reading material, but you have to mail me for that. So now furnace programming. So background absorption in GFAS can be minimized by either furnace programming or by background correction method. So what is a furnace programming? That is a very small one. For each and every sample, you have to do that. That is fixed for every sample. However, the background correction methods, you can use any one of them depending on your instrument, which facility is available. All the three, normally these two are very common, and you can use either of these two. And now this was not used very widely nowadays. So now let us see what is furnace programming. Now, when you are putting like 100 microliter of sample, you need to heat the sample in a stepwise manner, that so that at each and every step, your contaminant or whatever matrix elements are there, they should be removed. So now just start from when you are putting the sample. That time the tube is around room temperature like 25 to 30 degrees centigrade. Now you heat slowly to that tube to 100 degrees centigrade, and then like 100 degrees centigrade with a ramp you heat that and keep there for few seconds. So that step is known as dry. What will happen there? There all your solvent solution will be drying up, and that time there will be a continuous argon flow throughout the tube so that the solvent will be washed away. Now then you again give a ramp from 100 to a ramp to around 600 to 700 degree, which is known as pyrolysis temperature, and where again you put your sample for few seconds. Now what will happen here? Whatever organic material will be there or any volatile impurities will be there, they will be volatilizing, and again there will be an argon flow so to swipe away everything from the optical path. So now your sample will be clean. Now you increase the temperature suddenly within 1 second to the atomization temperature of your element. It varies depending on element to element, it varies. The atomization temperature can vary from 2000 to 2700 depending on the various elements. Say for aluminum it will be around 2600, but for cadmium it will be around 2000. So there is a variation. So you now you know what is your analyte, and that many a times the instrument itself will suggest you which heating method to be taken depending on the element. So you are choosing that, and then your final step, it will be hitting to the atomization temperature. During that time, all your analyte, whatever is the present in the sample, they will get atomized and they will be present in the optical path where the atomic absorption will occur from the holocathode lamp. And now your detector will be detecting the IT. So that case, now the argon flow will be stopped because you don't want your analyte to be swiped away. So argon flow has to be stopped there. So this is the temperature programming, furnace programming, through which around 90% of the background will go. But then whatever other background will be present, they can be corrected by these techniques. And there is another method of atom formation, that is the hydride generation atomic absorption spectrometry. So what is that? It is an alternative approach for elements like arsenic, selenium, tellurium, germanium, etc., which can form a volatile hydride easily on reduction. Now here a vapor of the hydride of the analyte is generated by treating the sample with NaBH4 with HCl medium. You know, acidified NaBH4 is very good reducing agent, so it will reduce the analyte into their hydride. Now this hydride can then be decomposed to an atomic vapor at a moderate temperatures without direct injection into the flame. So now the burner assembly in FAS is replaced with a silica tube which can be heated electrically by a coiled wire, where now I am giving the picture of this. Now you can see, now this is your sample reaction vial where NaBH4 will be is going there, NaBH4, and then there is sample. So NaBH4 addition, then it will be agitated, and now whatever hydride will be forming, they will be transferred to this flame and quartz tube here through argon or nitrogen. Whatever is there, you swipe all those hydrides to the quartz tube. And now there it is heated to around 600 to 700 degrees centigrade, where then again atom will form. So the hydride vapor is flushed by stream of argon into the tube where the temperature is sufficiently high, around 900 degrees centigrade, to atomize the vapor. Now the atoms are then detected by the beam from the source lamp which passes down the axis of the tube. Now here the atom cell is a flameless, but we can use a flame to heat the tube since the flame gases do not pass through the light beam. Now, what are the advantages again and disadvantages of hydride generation? No absorption from flame gases, very good, because flame is a rich spectra. All the decomposition product of your fuel, oxidant, and sample will be there. So it is a wide, like broad spectra of absorption. But in this case, no absorption for flame because your light is not passing through flame. No use of nebulizer and long residence time. Better detection limit and high sensitivity. Not all the sample metrics enter the atom cell like GFAS, and hence low background. Disadvantages is that efficiency of hydride formation depends on oxidation states of the metal. For example, antimony and arsenic, they should be present. They should not be present in +5 state. Only antimony 3 and arsenic 3 will form hydride efficiently with sodium borohydride. presence of some easily reducible transition metal elements such as cobalt, copper, nickel, etc. can suppress the hydride formation. So applicable to only for limited elements. So these are the disadvantages. Now there is another technique depending again on the principle of atom formation is cold vapor atomic emission spectrometry. So this method is exclusively for mercury because mercury has a high vapor pressure of atom at room temperature, and because of this elemental mercury vapor can be generated by reducing inorganic mercury compounds. The mercury vapor is flushed out by bubbling argon through the solution along a silica tube for analysis using a hollow cathode lamp of mercury. Unlike in case of GAS, there is no need to heat the silica tube in this case because mercury is already in atom form, and detection limit here is 2 ppb and wavelength used is 184.9 nanometer. The flame it is 0.2 ppm. You can see 200 ppb. So but the detection limit is very good for in CBAS for mercury. And wavelength use is 253.7 nanometer. There you cannot use 184.9 nanometer because in the flame all the other gases will be present, decomposition product of your fuel, oxidant, and your sample will be there, which may absorb in this range. Therefore, there you cannot use the 253 nanometer line. Now atomic emission. Now let us see the emission. All these are all about absorption. Now let us go into the emission spectrometry. So now here you don't require a source. Now you thermally you are heating your sample, and they are going to the excited state by thermally, and then they will, when coming to the ground state, they will be emitting their characteristic radiation. That is what we will be monitoring in atomic emission spectroscopy. So here the emitted wavelength is the identity of the element, emission intensity is concentration of element, is related. Absorption technique, detection limit depends on ground state atoms, whereas in case of emission technique, detection limit depends on the excited state atoms. Now the distribution of atoms in various states is governed by Boltzmann distribution ratio. You all may be knowing that is N1 by N0 equal to G1 by G0 exponential delta E by RT, and where R is the molar gas constant and T is the temperature in Kelvin, and G1 and G0 are the degeneracies of energy level. Now, so at high temperature, excited state is relatively more populated. So now you can see this is the simplest emission technique, the flame photometry. You may have known that flame photometry is used for alkaline earth metals, and even the flame test you are doing during your 10+2 level for salt analysis is nothing but emission technique, where you can see the barium gives a P green. So that is the nothing but the emission profile of barium. Now the typical sources, as we have as I have told you, there is no light source is required here. Here only a heat source is required. So and the different type of source used are flame, direct current plasma, alternating current plasma, spark, LIBS, plasma source. That is most important is the inductively coupled plasma, and this we will be looking into deep. All other you can find in some of the standard books. If you are interested, you may go through it. But the most important one is the inductively coupled plasma, ICP OES, which is known as ICP OES, that we'll see in bit details. Now here I have given some pictures. You can have a look. This is the flame. This is the direct current plasma. This is the alternating current plasma. This is the spark source. This is the LIBS. This is the plasma source, and this is the microwave plasma. So just have to have a look. Now what are these? Just let us see one by one. The direct DC arc, which is known as DC arc or direct current arc. It is two solid electrodes will be there. One electrode supports the sample. High current around 5 to 30 ampere, low voltage 10 to 25 voltage discharge operating in air. Arc temperature normally reaches up to 4000 to 6000 degree Kelvin. Now the resulting plasma of high velocity ions, electrons and atoms produces the atomic emission spectra. Now you can see the cup shape electrode to support the sample. Here sample will be supported. High purity graphite is a popular electrode material, and if the sample is a metal, it can be cast as a electrode itself because that is a conducting, because you need your electrode to be a conducting one. So for non-conducting sample you are using graphite, or for conducting sample then you can graft make the sample itself as your electrode. Now AC arc, two solid electrodes, one electrode is supported in the support the sample, again same like DC arc. high voltage around 2200 to 4400 volt, or both the case you can do it in low voltage and high voltage also. Now the arc ceases at the end of each half cycle as the applied voltage drops below the value needed to maintain the arc. So now electrode temperature is lower for AC arcs than DC arcs. AC arcs has the advantage of better precision over DC arcs, as the electrode can spot from various positions at a rate of 120 times per second, and then finally you can take an average. However, it is less sensitive than DC arc. So this is the arc source. And however, precision are very poor in this type of arc system, like 10 to 15% are the general precision, and therefore they are not very popular. Spark source, it contains high peak current, and here you need the sample as a flat surface where you can make a spark, and then again it will some atoms or ions will be forming that can emit their characteristic wavelength, which can be detected. Now LIBS also operates by using a pulse focus laser, and it is laser induced breakdown spectroscopy, that is LIBS. Focus laser that is fired at a sample with sufficient pulse energy so as to create a plasma around the area struck. Now bound atomic electrons are striped from the atom comprising the material. So as the plasma cools, atoms recombines with electrons, and in the process emits light in the UV, optical and IR regimes, which can be very well detected. So these pictures I have taken from some standard books. Now, advantage of ICP. So as I have told you, ICP is the widely used source. So what are the advantages? Why it is so widely used source for atomic emission spectroscopy is that it is simpler to operate than the arc spark sources, especially for solution samples. So, and you know that for each material we can make it a solution. And also there are solid sampling technique which can be associated with the ICP, like laser ablation and all. So lack of electrodes and hence freedom from contamination and low background, high temperature around 10,000 degree Kelvin approximately, and hence low chemical interferences, simultaneous multi-element capability over 70 elements, including even you can do the non-metals like phosphor and sulfur, low background emission and relatively low chemical interferences, high signal stability leading to excellent accuracy and precision, excellent detection limit for most elements, wide linear dynamic range, 4 to 6 order of magnitude, applicable to refractory elements also, as the temperature is quite high. So chemical interference is not there. So oxides will not be stable there. They can go back to their atom level. Now, what are the various components needed to produce a plasma source? Is that a plasma torch is needed? This is the plasma torch. This one is the plasma torch. Then a radio frequency coil, RF coil is needed. This is the radio frequency coil, this one. And then RF power supply is needed. So now plasma torch consists, now how that it looks like is that it consists of three concentric, this is a cross-sectional view of a plasma source. It consists of three concentric quartz tubes. Argon used to form the plasma is passed through the outer tube at a flow rate of 12 to 17 liter per minute. Argon used to change the base of the plasma relative to the tube, and the injector is passed through the middle tube at a flow rate of 1 liter per minute, and even the argon along with the sample will be passing through the middle of the plasma tube at a rate of 1 liter per minute. So these are the various temperature zone in a plasma, and normally the normal analytical zone is 6000 to 6500 degree Kelvin. Now how a sample is introduced into the plasma? It is nebulizer. There are various types of nebulizer, like produced on an aerosol. In ICP, two forces are used to break off to a liquid into an aerosol: pneumatic forces and ultrasonic mechanical forces. Most commercial instruments have pneumatic nebulizers. The difference in pneumatic nebulizers in FAS and ICP-OS is that in case of FAS, the gas flow is in the order of 10 liter per minute, whereas in case of ICP-OS, it is approximately 1 liter per minute. So there are primarily three types of pneumatic nebulizers are there: concentric nebulizer, then cross-flow nebulizer, which are very good for high salt content samples. You can go through it. All the details are written here. So it is for high, like if your sample is having very high salt content, then this can be used. And for the Babington nebulizer is for either viscous samples or oil type of samples can be done, and even high TDS samples can be done here. Then ultrasonic nebulizer. So all those above are pneumatic nebulizer, and another type is ultrasonic nebulizer. That the liquid sample is formed into an oscillating piezoelectric transducer, where the oscillations break the sample into fine aerosol. So aerosol formation is independent of nebulizer gas flow. Now the efficiency is around 10-fold greater than normal pneumatic nebulizers. So it is a very good like nebulizer. Now, once the nebulizer forms the your mist or your aerosol, it has to be passed through a spray chamber where heavier particle will go down to the drainage, and only the particle of having size less than 1 micrometer can pass to the plasma, because plasma may the stability of plasma is very much dependent on the sample whatever you are introducing into it. So if the sample size will be very high, then it will shut down, plasma will shut down. So therefore, it is very much, you have to ensure that the aerosol only fine particle will go. So after the nebulizer, they will be passing through a spray chamber, where they will be further dissociating into rather small particles, and then they will be moving into the source. And as I have told you, like this is normal ICP-OS can take solution samples. However, there are attachments to ICP where you can use solid sample also, like hydride generation, graphite furnace, and laser ablation. So these are the various attachment where you can use. In these two cases, very well you can use solid samples. Now, sampling from plasma, the emission can be sampled either radially from here or axially. So these all things I'm just giving brief idea, because it is very difficult to complete all this techniques in just 1.5 hours. So I'm just giving you gist of the things, so that you can go through a standard book and find out if anywhere you are you get stopped or you are not understanding something, you can mail me at my mail ID is provided in the first page of the slides. Now, what are the various type of interferences in ICP-OS? Thus, again, here also, as in case of AS, there are various types of interferences: simple background shift, sloping background shift, direct spectral overlap, and complex background shift. So this you can see, I have just pictorially I have shown it here. This simple background shift. So now you can see that in case of the simple background, because 1000 milligram per liter aluminum, say this is tungsten, you want to determine tungsten in aluminum. Now in a normal your standard, the baseline is here, but when you are passing aluminum, in which you are going to determine tungsten, then your baseline is lifted. So now how the sample will look like? The sample will be sitting here. So now you have to subtract like this. This is not required for you, because this contribution is from aluminum. So you have to subtract that. So what will do? You just take 1000 milligram of aluminum and then take it as a blank and then do it. So sloping background shift is just like that, where you can take a 2 point. When it is placed in a sloping background, you can take a 2 point correction. You mark here, and then take the peak area. So now direct spectral overlap also is there. When it is direct spectral overlap, then you have to either do the IC in technique, the contribution of the interfering element to the analyte emission intensity is corrected by measuring the emission intensity of the interfering element at another wavelength and applying the predetermined or calculated some mathematical calculation you need to do, and then you can do it. Otherwise, you can use a alternate line. So this is also another type of, say this is the analyte, this is blank, and this is matrix. So now your signal will look like this. So you need to follow some mathematical calculation to deconvolute the signal and then do the background correction. So in this case, in this type of where the background is very complex, anyway you need to choose another line. So that is what background correction. So now coming to the mass spectrometer. Again, the mass spectrometer is nothing but where now you are not measuring the photons, either absorbing photons or emitted photons. You are not measuring photons, but you are measuring the masses itself. So now, as you know, mass also is a identifying factor for any element. Say for sodium, if I'll tell you sodium, then its mass is 23. If magnesium, then 24. So different element, their masses will be different. Therefore, mass also can act as a basis of identifying and quantifying these elements. So an analytical technique to identify elements or molecules based on their M/Z ratio is where mass spectrometer. This is a typical block diagram of your mass spectrometer. Sample inlet, now it is ion source rather than atom source. It's the ion source, then mass analyzer to separate the masses, then detector, then signal processor. So for inorganic, there are two types of mass spectrometer: inorganic mass spectrometer and organic mass spectrometer. Inorganic mass spectrometer, you will are capable of doing the elements, whereas organic mass spectrometer are used to detect the organic molecule itself and the structure elucidation and all. So for inorganic, these are the various excitation, so like ionization sources, and for where again the ICP is the most rather the most widely used one, and TIMS also, GDMS also are used. So GDMS totally for solid samples and TIMS for isotopic ratio measurements. Normally they are used, and for all other normal work, normally people use ICP-MS. For organic mass spectrometer, as you know, organic mass spectrometers are for elucidation of structure, so that it can also be used for quantification purpose. So now these are the various ionization sources for organic mass spectrometer. Now, how it is get ionized in a mass spectrometer? How the samples are getting ionized? Either charge transfer, thermal, or panning ionization. Now, the various mass analyzer, once the ions are formed, now your sample is a complex matrix. They are all type of ions are present there. So you need to separate these ions. Otherwise, your detector will not be able to identify which signal is for which mass. So now, before reaching to the detector, you need to separate all those masses. Like in optical spectrometry, monochromator is there, which is responsible for separating the wavelengths. Your mass analyzer is responsible for separating the masses. So what are the various types of mass analyzer? It is either magnetic sector, quadrupole analyzer, time of flight, ion trap, and ion cyclotron. So these are the various types of mass analyzer. And what are the various types of detector? Either Faraday cup, which are normally used in isotopic ratio mass spectrometer, or you're in TIMS, thermal ionization mass spectrometer, which is dedicated for your isotopic ratio. They are normally used on Faraday cups. Then electromultiplier, mostly used in ICP-MS and other cases, macrochannel plate, and induction used. So these are the things. Now here also there are various type of interference is possible. Even mass is a now here we are monitoring the mass, which are different for different elements. However, there are isobars. You must know that there are isobars. So cadmium and indium, they can come at the same point. Tin and indium, argon and calcium, nickel and iron. So these are the isobars. So if they are coming at the same point, so these are the isobaric interferences. Now there are polyatomic ion interferences also. Whenever you are passing through a plasma, like it is normally ICP is a argon plasma. So there your solution contains oxygen, hydrogen, because it is a aqueous solution. So now this type of things can form. So you can see argon oxide, the total mass is 56, which can very well coincide with iron 56. So these are the polyatomic ion interferences. And oxide and hydroxide interferences are also of similar type, like any other component present, say titanium and nickel. You are analyzing nickel, but then if it is a titanium alloy, then very well titanium oxide will interfere with nickel. So like that, other things are also there. So in a rare earth, say in case of a rare earth element, once I have faced this issue, we are doing a rare earth matrix in which we are identifying ytterbium. So we could not do it because gadolinium is present at a higher level. So you can see all the gadolinium oxides are overlapping with each ytterbium spectra. So when gadolinium is present at a higher amount, so they have a very good contribution at the ytterbium spectra. So it is very difficult, this type of, sometimes when there is a free of interference mass, you can take that. But in this case, there is not a single mass of ytterbium is free from interference from gadolinium. All its oxide, gadolinium oxide, coincides with the ytterbium one. So the matrix interference also is there. So all those things, whatever you have seen are spectral interferences, and metric interferences is noticeable at when your matrix or concomitant concentration is greater than 1000 ppm, which can be easily eliminated by using an internal standard. So now let us compare all these AS, ICP-OES and MS. So you can see that AS is a single element. It can analyze in ppm if you are taking a flame, or ppb for others like GFAS, GAS or CBAS. The capital cost is low, as well as the running cost is low. Simple, but the small dynamic range. GFAS about 1000 times more sensitive than flame AS, but also more challenging. Now ICP-OES, multi-element, PPB range, limited spectral interferences, good stability, low matrix effect. Whereas in mass spectrometer, multi-element, possible to reach to PPT or even PPQ level, you can go with a mass spectrometer. Most complex, most expensive, low detection limit, and isotopic analysis is also possible here in case of a mass spectrometer. So this is what all about this class. So now I have not yet received any mail or any queries from you people. I think it is very clear. The classes are very clear. So it all will be knowing at the time of your exam and your interview. So please, if anybody is having any queries, then kindly mail me so that in well advance I can clear your doubts. Thank you.